everybody. So let's crack on. Have you got your coffee? Lovely. And so we are doing. I need my overhead. We are doing 2.3. So here we got 3 bars. Okay, made out of steel. There's a 15 load being applied, 15 kilonewton load being applied here. Determine the force developed in each bar. What else have we got here? A, B, E, F have cross-sectional areas of 50, and CD has cross-sectional area of 30 millimeters squared. So if we don't have enough problems, they've made the bars different lengths. So we're going to have to make start to make some assumptions. Okay. When you tackle structural problems, and the assumption that I'd be making here is that this is going to be a rigid bar with no bending. It's a girder, so it's safe to assume. And these bars will in effect behave very similar to springs. So I'm imagining that this load is going to be pulling down. This rigid bar will then cause this one to extend, this one to extend a little bit, and this one possibly to contract. So I imagine there'd be some sort of cantilever, well, seesaw effect, pivoting effect around there. Right. So I started off by, what did I do? I started off by taking a cut through the entire system here, and the cut that I took through was to take, notice I've got 3 of them, so that almost makes me feel like I'm doing a method of section. So I'm going to cut through these 3 bars here and expose the internal forces. So I've got a free body diagram which looks something like this. This is going to be my FA. I'll name it after, I'll treat these a bit like nodes, so I'll name them after those things there. So we've got FA, FC, and FE. Then we've got this solid bar, and then we've got this load of 15 kilonewtons, or working kilonewtons. Right, so that is my first equation that I can do. I can do a sum of forces in the y direction, take things to be going positive, and so we can have FA plus FC plus FE equals 15. So that would be my first equation. Next equation, I could take sum up forces in the x direction. See, I'm not going to get anything, so I'll jump over that. So the next equation, I will take moments. So I'm treating this just like a framework problem. So it makes sense to take moments at one of these points so that we get rid of an unknown. So let's take a moment at the C point. So we'll take moments at C, and we'll go around clockwise. If you go back to your beam here, you notice that's 0.4 from going from there to there. These are distances of 0.2, 0.2. Alright, so what does that give me? It's going to give me a minus, we'll start here actually, so that's a positive 0.4 FA. No, it's not 0.4, is it? Yeah, 0.4 from there to there. Here we've got a distance of 0.2. That's going now negative, minus 15 times 0.2. Okay, this is my pivot, and now this one here, that's going to be negative as well, minus 0.4 Fe equals 0. Okay, so let's try and leave this in a nice form to use later. So I'm going to multiply through by 5, I think. Okay, so then that gives me 2Fa multiplied by 5, that makes it into 15. Do you like the close-up? I don't know. That's 15. And we got minus 2Fe. I think you're a bit too close. Right. Okay. So we've got equation 2. Now, taking forces, taking moments, all very good. You can do that without thinking. This is where you have to put your thinking cap on. It's a bit like with the indeterminate hinge problem. We had to think, well, what could be our additional equation? So notice here we've got 1, 2, 3 unknowns, 2 equations. We can't solve it. So we need another equation. And it's going to be based upon something a bit like the indeterminate thing, something where we're taking in the geometry, or something about the structure that we can make an assumption about. So what can we make an assumption about here? As I said, we're going to make the assumption that this bar is rigid. These members we're going to assume are acting a bit like springs. Okay, so we are going to assume that when we apply that load, that this FA is going to get slightly stretched. This one here, because we're applying the load here, that's going to get slightly stretched as well. So, or I would guess it would do anyway. So let's say that's the original length. Whoops. And here, this bar here, we imagine is going to get slightly squashed. Okay. So that will be where the bars end up. So from my displacement, I've got displacement A, displacement C, and then a displacement which is going to go in the opposite direction, will be a negative, which will be E. So what can I do? Well, you can do some sort of geometry type rule here. The simple mind's interpretation would be that I would expect the C, for this to be rigid, to be the average of the displacement A and the displacement E. Okay, so that would be the way I would interpret the problem. You can do it other ways. You can do it using similar triangles and whatnot, and try and be a bit more jazzy, but that seems to work, because what we're saying is that if this is going to move down a certain much, that's going to move a certain much. C is going to be in the middle, so therefore I need to add these two up, average them, and then we'll be in the middle. So that's all we have to do. So we've got that, and then we can apply our rule that F L over AE. So that's the next thing we need to apply. This time we're going to apply this rule, but we'll apply it for each individual section and see how the internal forces in these bars will then change. Okay? So I've been swimming. Right, so what do I need to do here then? So I'm going to take the, get rid of that, get rid of that. I am going to take C, and then the original length of the bars is all going to be the same, so I'll call that L. The cross section of the bars unfortunately changes, so they've been a bit nasty to me there. So this C bar is the thinner one, it's the 30. Right, so we don't have to worry about units too much, just put 30 in here. E. Right, so that is my C term. Right, let's replace this one here. So it's the internal force in A. Its original length is going to be L. I mean, we are told what these L's are, but we don't need them, I don't think. And A is a thicker bar, 50 millimeters squared. And then we've got the last one, FE. L 50 millimeters squared E. Okay, so I want to rearrange this. What am I going to do to do that? Well, what I did was I multiplied out by, what would it be? I'm thinking it'd be 300. So I multiplied everything by 300, which left me with 10 FC equals, so 2 times 50 is 100, so yeah, 3 FA plus 3 FE. Okay. Yeah, I'm definitely too close, aren't I? You don't want me that close, do you? Okay. Right. So that is fine. So now I've got my third equation. So my first equation is FA plus FC plus FE equals 15. That's equation 1. Second equation is 2FA minus 15 minus 2FE equals 0. That's my second equation. Well, I mucked around and solved it. So I took the what did I do next? I took equation 3 and substituted it, or rather took equation 1 and substituted it into equation 3. So that gave me 10, 15, take away FA, take away FE equals 3 FA plus 3 FE, and so rearrange that and you end up with 150 13FA plus 13FE. That's your equation 4. So now we're looking at equation 2 and 4. And what did I do there? I took equation 2. Now I took this equation and then I doubled it, and then I took this equation and multiplied it by 13. Added those two together, and that then got rid of my FE. And you end up with FA equals 150 divided by 13. No, you don't end up with that. You end up with, well, I'll just tell you the answer. You end up with F okay, so I didn't do that. I must have took one from the took one away from the other, because I ended up with 105 equals 52 FE. 52 FE. Okay, sorry I'm making a mess of this. So FE equals 2.2 kilonewtons. Right, so combine those two together. As I said, multiply that by 2, multiply that by 13. Yeah, exactly. I must have taken that over the left hand side, and then that will give you your FE term. Then when you've got your FE term, it's just a question of back substitution. So I'll let you work that out at your own pace. So you can substitute that into that one. And you'll find that you should get FA equals 9.52 kilonewtons. And then you could go back to, let's say, equation 1, be the most obvious one to use. And then you'd find FC equals 3.46 kilonewtons. Right, so let's have a look at our final solution. So A is 9.25, FC is 3.46, and FE is 2.02. And then we've got the 15 coming down here like that. So, does that look correct? Well, yeah, we'd expect more stress to be in there. Although we do have a thicker bar, so potentially that could have been less stress than that one. But that's moving a lot less, so that's why we got less stress in the middle bar. Right. Have we done everything we want to? If the applied load determine the force developed in each bar. And that's it. So we could now go on, although we would have to look up what the Young's modulus is, but we could then work out the change in lengths for each individual bar. So that's the final thing we could go on to do. Other than that, I think 2.3 is done.